Hi, my name is Amari Owens, and welcome to my Physics Lab 2 um, on Physics 2111. The purpose of this lab is to observe the properties of projectile motion through different methods of observation. One method of observation was compiling data through the observation tracker program software that takes real world videos and tracks their motion. The second method of observation was to create a computational model through Go script Python code. We will use both methods of observation to explore kinematic equations. What is kinematic equations? Kinematic equations are equations used to predict motion using information like time, initial position, final position, and initial velocity. We can also use net force and mass to derive acceleration. Using these properties helps us predict things like projectile motion and constant motion. Now, I will now introduce my system and my surroundings and my initial conditions in this experiment. My system is the paper ball that I'm using, and then my surroundings were the flat surface that the ball was thrown from, and the airspace affecting my paper ball. There's a meter stick in the background acting as my measurement, my overall measurement for displacement of the ball. Here we go. I will show you now a demonstration of the video.
Okay, just do it.
My procedure is that I first record a video of me throwing the ball in the air, and then I sent the transferred video to the tracker software program. I then analyze that data from the tracker software program, and using that data, I calculate the initial velocity to help put together my computational model. I pulled the starter code from my lab assignment using my initial velocity from the tracker software program, and then I created the iterative predictive model that we had learned to implement in Lab 1, which basically just calculates um, force, velocity, and then position, and then just repeating that steps while incrementing time. Here is a comparison of my tracker data against my model. In the blue, we have the tracker data, and in the red, we have the model. The model is a little bit more smoother, as I believe the time increments are a little bit more consistent along with the model, while we have the tracker data, which is a little bit more less inconsistent, as we can only track the motion through the frames of the data. And I also believe there are a little bit more like changes in initial velocity for the tracker data compared to the model. So that there's something also to consider in that sense. And then here is a velocity time graph of my model that shows it with drag and it shows it without drag. Virtually the same. Some potential sources of error was maybe in my inconsistency for accounting for drag, and potentially that's about it. Now I'm going to answer some questions that were proposed. Um, one question asked if my object experiences terminal velocity, and it asked me to look at my velocity versus time graphs. Well, if we look at our velocity versus time graph, terminal velocity is basically when you're falling through the air and you reach your final speed before you hit the ground. But the thing is, in order to reach my final velocity, if I reach my final velocity, from that point on, it would be constant, practically a straight line. But as you can see in this model, it always goes down. So that means the velocity is always changing. Probably at a constant speed, but it's always changing. So no, I do not reach my terminal velocity. Probably an idea of reaching my terminal velocity would probably just be throw it from a larger height. Another question asks if I threw my object straight up with the same initial speed, would the time it takes to reach the ground be the same, longer, or shorter? I said it'd be shorter because the initial velocity, while it would be the same, they would not be going in the x direction as well. So the amount of time for it to take to hit the ground would be much shorter. Thank you for listening to my presentation, and I hope you enjoyed it. Thank you.